Whatever we have covered so far, DFT wise, any questions you guys have, then I'll try to answer those. Huh? No. I'm not saying. I'm saying right now that I'll come to. What I'm saying is right now, if the material that has been covered and sometimes slides have been shown, if you think there are gaps which you could not follow, you tell me the questions, I'll write them and then try to answer. RPA. Okay. So, if I do it, I don't think you will follow it right now. RPA takes a little long. Because if I do the whole thing, see what, so I can give you a nutshell if you want. What the RPA, the way it came from is the wave function for a many electron system, the Hamiltonian, was divided into two parts. The long range part gives a collective oscillation, which is a plasma oscillation. And short range part is something else. So short range part you can do perturbation theory. So one did this, quantized the long range part as a harmonic oscillator that gave you plasma, and short range part. And when one did the perturbation calculation, one ignored the phases between the plane waves and said wherever phases are random, you can integrate them to be zero. That was the random phase approximation, the phase of the plane waves. So, but it requires some time. It's a little long. So right now, the only thing people say is that you ignore FXC, that's RPA. That's basically saying your starting point is plane waves or non-interacting system. Huh? Right now, the RPA people say that you start with non-interacting system and the perturbation you put only the direct interaction. You ignore the exchange and correlation. That's what it is. But that's equivalent to the, showing the equivalence is little, it requires a little working out. Huh. Yeah. Yeah, so keep your questions short and precise. I'll understand you. If you, I need explanation, I'll ask you. In a solid, there is no self-interaction because the volume is infinite. Each charge has zero energy. Smeared over the entire volume. Yes. No. Exchange is reduction of interaction between two electrons. It's a two electron effect, not a single electron effect. No, I can't imagine. I calculate it and it comes out to be non-zero. So, exchange energy as exchange correlation energy is not a direct interaction between an electron and another electron. It is an electron and reduction of density around it, which is known as the exchange correlation hole. Which is centered around the electron and its radius is roughly Rs. So this is not spread over the entire thing and this is finite. Okay, the correlations are such that the exchange correlation hole is centered around the electron and its radius is roughly Rs. So you can see that the energy is going to be of the order of 1 over Rs. I thought I answered your question already. Electron does not have localization. Electron is moving around, but it has a thing stuck with it. If you have the shirt stuck with you, doesn't mean that you are localized.
Let me just directly ask. So in metal, when we say nearly free electron, does the exchange correlation hold? Is it still
Yes.
or is it
Yes, let me also directly say yes. YES, capital. Yes. Other questions? No, you're not, you dissociated yourself, so you're not supposed to speak. And he's my student, so I'm favoring him. No, you're not supposed to speak. No, question asking is ask a good question. Think, appreciate it. No, you get only once. Like that movie, Bond movie, you live only twice. Other questions? Could you speak louder, please? Yes. Okay, GW I have not worked out, and GW is little long. So basically, the whole idea is that whenever in many body theory, when you write a Green's function, right, the poles of the Green's function give you the excitation energy. That's the whole idea. Then the whole thing is that the electron-electron interaction is screened by the dielectric function, and then you write the whole thing. So that's the whole idea. I mean, but working out requires a little more. Questions? I would be happy if these boxes get empty. But he's not. They are not even asking questions. I want them to speak. What is the difference between? Okay, so that is something very nice. So I'll work out because that is one thing on the agenda. So one is, so let's talk about the response function, right? So one is Dyson's equation. Dyson's equation is basically, if you want to get a response function, how you can get it iteratively, right? So you start with non-interacting system, all right? So if I have a non-interacting system, let me explain this. So suppose I have a cone-sham system, del square plus, V external, I'm write it explicitly, plus V Hartree plus V exchange correlation, right? And I have, this is my zeroth order, phi I0 equals epsilon I0 phi I0, right? And now I perturb it. So in perturbing, what do? I write this 1/2 del square plus V external plus V Hartree plus V exchange correlation plus some V external first order, let's say, phi I0, phi I equals epsilon I phi I. Everything changes, but we want to do it perturbatively. So we'll keep it only first order. Now what happens, think about it like this. This external potential changes the density of orbitals, and so V external 1, the perturbation, gives some delta phi, right? That delta phi gives you delta rho, right? That delta rho changes V Hartree and V external, V exchange correlation, where they depend. So this, therefore, in the first order perturbation, it's not just V external that you're changing the whole thing. So what you have is minus 1/2 del square plus the initial one, right? V Ks 0 plus V external 1 plus V Hartree 1. I'm just doing first order. Xc 1 phi 0 plus phi 1 equals epsilon 0 plus epsilon 1, right? Now what you are trying to, this again has to be self-consistent, right? So now let us write it in a mathematical way, and that is, if I write the response of a system chi r prime as equal to change of the density in terms of V external, right? This I can write the V external at r prime. This is what gives you the non-locality. If you change potential at r prime, density at r can change, right? This I can write by using the chain rule, is delta rho r, and I have Pratim Singh in mind. He said, I must ask you to calculate the functional derivative once times delta Vks r double prime over delta V external r prime, and I integrate over r double prime. Is it clear so far? This is just like the chain rule in derivatives. I am doing a functional derivative chain rule. All right. Now you can see what is Vks. Vks is this plus this plus this. This I do not know in terms of external potential. So I'll write it in terms of, I'll do one more chain rule. I said V external changes the density and density changes this. So I'll write it in terms of the density. So I'll write this further as integral delta rho r delta Vks r double prime delta Vks r double prime over delta rho some tau vector. I'm running out of vectors. I don't want to use too many primes. Delta rho tau over delta V external r prime dr double prime d tau. Are you with me? Now I used one more chain rule. This I broke again. All right. Now you can see what this is. This is chi 0. That is change in the density with respect to the total potential of the non-interacting kind. So this is non-interacting part, which can be calculated by summing over the orbitals r double prime, right? This is nothing but Vks. Okay, now I could have done one more thing. I should have done that. I'll just do one more thing out here. So this is the fun part. So instead of this, what I'll do, I'll break it, this I'll write as, just give me a Hartree exchange correlation, and in between I'm going to put in a delta r double prime minus r prime plus. So let me explain what I did. I wrote Vks r double prime as V external r double prime plus V Hartree exchange correlation at r double prime. All right. This derivative with respect to V external I can take, because if there is a function f r, for example, its functional derivative with delta f r prime is how much is the change when I change it at r prime. It can change only at r prime. This comes out to be delta R minus R prime. Okay, I've used that, and Hartree exchange correlation I've written like this. Is that okay? All right. So I can write this as, so I'll erase this. This is chi 0. Chi 0 R double prime multiplied by delta function integrated over, okay, so this will be R double prime here, and rest is with everything else. So that will give me, I'm just a bit messy here, chi 0 R prime, that comes from this and the delta function, there is no tau in this, plus chi 0, that is still there, R double prime integral. Inside, what is V Hartree? V Hartree is integral rho R over, now this is, I'm writing V Hartree at R double prime, so let me write this as R double prime, R, some function S over R double prime minus S ds volume. So if I were to take now by definition delta VH R double prime, when I change this is going to be delta rho S over R double prime S ds. Right? Change in a function, when you change the other function, whatever is left inside gives you the functional derivative. So delta VH R double prime over delta rho, and I'm taking it with respect to tau. So I could have written this tau, it doesn't matter, is going to be 1 over R double prime minus tau. Are these steps clear? By definition, if I have a function, and then we calculate more, if I have a function or functional f of function is equal to some g of f dr, then delta f will be equal to integral whatever functional derivative delta f dr, whatever comes here is the functional derivative. That's the definition I've used. He gave you an explicit formula, and I'm just using that definition. So I'm going to get here this, right? This part we have taken 1 over R double prime minus tau, and then next part is exchange correlation, and that is known as the kernel. I'm writing exchange correlation, derivative of exchange correlation potential with respect to tau. So this is going to be R double prime tau. Okay, and what is this? This is chi again. Chi tau R double prime dr double prime d tau. R prime, it is at R and R prime. No, but there was a delta, there was no tau in this. The tau came because of this. This part was already taken out. So let me, okay, we make it slightly better because I ran out of space. So I should write it as this, and let me write it here, integral delta rho R over delta V Ks R double prime delta R double prime minus R prime dr double prime plus. Now you see this is known as Dyson's equation because this is precisely how the Green's function is written in many body theory. You write a Green's function of interacting which is G0 plus G0, some interaction term G. So now if you want to approximate it as a first approximation, I can take this to be chi 0, put it here. Whatever next I get, I put it again. So it becomes an iterative perturbative series. And you can see the picture I was trying to make. You take this multiplied by V gives you change in the density, right? This was this. If I change external potential, it changes the density. It changes the density, and therefore, with this, it gives you the change in the potential, the Hartree and exchange correlation potential. So it gives you that change, and that change changes the density again through non-interacting, and this is from the external part itself. So this is precisely this picture written mathematically. All right, this is the direct Dyson equation kind of thing. The one that was used by Arun yesterday was the inverse one, and that was this. The inverse one was like this. He used chi inverse, and when I write chi inverse, this is change in the potential with respect to the density. It's inverse of that. All right. So what he wanted to know is what is the change in the external potential at R with respect to rho at R prime. All right, which I'll call chi inverse R prime. All right, which I can write V external is what? It is V cone sham minus V Hartree minus V exchange correlation, right? At R, and I am taking its derivative with respect to rho R prime. Is that right? Can you quickly tell me what this is? This should be easy. What is the first term? What is the first term? Derivative of V cone sham with respect to the density. What is that? Chi 0 inverse R prime. What is the second term? Look at that, I just calculated it. Hartree kernel. So that's 1 over R minus R prime. What is the last term? Right? And this we have done in static. There is no time dependence. Suppose there is an omega dependence within certain approximation, I can write this. Omega. Right? All this goes to omega. This is omega. Omega. This should be omega dependent, but we do that adiabatic approximation, keep it like this, and this is all omega. At resonance frequency, this fellow blows up. And that's what is used in writing those TD-TFT exchange, the excited state equations. Yesterday you saw Kasida's equation. So you say that this is going to blow up, right? So its eigenvalues, you write this as an eigenvalue equation, that should be 1. Those were written as the Peter-Silka equation with Gross. Kasida used it in a different way, and he wrote those equations, other equations, right? So that's what it is. If you take chi to be just the first, that first order perturbation theory, only first one term, then you get a single pole approximation. You can get from here the excited state energy delta E equals delta epsilon plus an integral of chi 0 and orbitals involved. Okay, but that comes all from here. Basically, idea is that a response function blows up at the correct frequency. Okay, This will blow up. Chi naught will not blow up. Chi naught is not the exact response function. So using that one makes a equation. Does she deserve a chocolate? Yes? No? Okay.
So you are giving the answer. So you need it.
There, she started it off. Yeah. And he also answered, so he also deserves it. You answered, so. Any questions? Yes.
In this, when we take omega, so we are taking this kind of adiabatic approximation sort of thing.
It's an adiabatic approximation in a different way. You are making the potential, the time dependence to be very slow. So at each time you say, whatever the density changes at a certain time, it changes the potential at that time itself.
So this is not applicable for very fast changing.
Of course not. Of course not.
Light is not treated this way.
No, light is okay because light is roughly 10 raised to 15, right? No. The time scale there is much faster. It's okay. It comes out to be okay. And you have the other thing is you have no other choice to do it. That's the other thing. People have tried. For example, in this you don't get double excitations. So that's a problem. Other questions? So all the fundamentals are exactly the same, not more than 7, 8 fundamentals. It's just that how you work it out. Other questions?
This might be a way. I will understand how that
Ah.
how will the harmony exchange in the exchange, like how do you make the hybrid functions? That connection is not very clear.
Very good question. Okay. So that's the other thing I had in mind. So let's do that. So how do we do the adiabatic connection, right? Okay. So I'll work out in detail because this is at heart of many things. So 2-3 things you'll need in this is going to be, one is Hellman-Feynman theorem, and I'm writing HF because I don't remember the spelling of Hellman. I'm just kidding. I know. So Hellman-Feynman theorem says that if I have a Hamiltonian dependent on some parameter lambda, and I solve this equation h psi lambda equals E lambda psi lambda, and just plain normalization of psi, it comes that dE lambda d lambda equals psi lambda dH d lambda. I'm assuming there is no other parameter, so I'm writing the full derivative. All right. Now, in adiabatic connection in DFT, we do a very special kind of lambda. So, what we write is we write the Hamiltonian as that kinetic energy Hamiltonian. Let me write it in detail. Summation I 1/2 del I square, all right, plus V external, and write it capital because it has all those R1. So, I'll just write it. Summation V external Ri, and I'll change it a bit, plus lambda VEE, and this I'll write lambda, and this lambda is going to be between 0 and 1. I change this, I take some other lambda, so I'm scaling, right? Scaling lambda from 0 to 1. And at the same time, I change this external potential. And I change this external potential So V external lambda is adjusted so that the density remains the same. All right? And by the way, so I'll come to that constraint. So you can write an algorithm to find that V. Okay? And that can be done very easily. So we have also done it. So it's not just in the air that one is saying that V lambda, you can actually create that V lambda. And by creating those V lambda, one can do the adiabatic connection study. Okay. Now, let's just work further. What is dH by d lambda? There is no lambda dependence here. Lambda dependence comes here and here. So I can write this as V external lambda d by d lambda. I'll just write in short notation plus VE. Is that okay? Now notice here, on the side note, lambda equals 1 corresponds to the true system. Right? If I take lambda equals 1, V external becomes my true V external, density is the same. And at the same time, so let's put it in the box. Lambda equals 0, that means I have removed the interaction. So it has become a non-interacting system of the same density. What is that system? That's the Cone-Sham system. Is the Cone-Sham system. And that has H Cone-Sham phi I equals epsilon I phi I. Right? This has orbitals. This has H psi equals E psi. All right? That difference is important. So I'm going to have psi lambda dH lambda over d lambda psi lambda equals, this is a multiplicative potential. So this becomes, and this gives the same density. So this will become V external lambda R rho R integrated plus expectation value of VEE with respect to at this psi lambda. Okay, let me write this once explicitly and then we can. All right? And this is dE d lambda. Therefore, E, if I integrate dE lambda d lambda 0 to 1 is going to give me, No, that's it. That's it. D lambda by d lambda. First term. Yeah. Same. All right. This is going to be integral rho r dv external lambda d lambda 0 to 1 plus integral VEE lambda d lambda 0 to 1. All right. This gives me E, the true E, minus E Cone-Sham is equal to, density remains the same. So I can, and this is independent of lambda, so I just integrate this. So this gives me 0 to 1 rho r. At lambda equals 1, it gives me V external, the true one, minus integral R. What is V lambda V external at 0? V cone sham. Plus, I'm going to write this because VEE psi lambda anyway gives me the same density throughout. So I can take out the Hartree part out because the density remains the same, and rest I'm going to write as EXC lambda, where EXC lambda is going to be VEE lambda minus E Hartree. Let me see if there are any questions. There will be an integration over dr. Yes. If I have a cone sham system with this, what is the E0? I have a non-interacting system with eigenvalue 0 to n filled. What is this energy? Non-interacting system. What is the energy? If I have a non-interacting system, minus 1/2 del square plus V, let's call it V0, phi I equals epsilon I phi I, and I fill n orbitals. What is the energy? Hydrogen atom, if I fill n electrons, what is the energy? What is the energy? I am taking non-interacting electrons, filling them in energy value, all the orbitals. GW कर लेते हैं लोग, GW कर लेते हैं. What is the energy? Chi भी कर रहे हैं, chi inverse भी कर रहे हैं. That's it, summation of epsilon I. So I'll just write this. So this is summation of epsilon I. So E becomes summation over epsilon I minus integral rho R VKSR dr. I'll put it in the bracket, plus integral rho R V external R dr as this term, plus E Hartree plus, or this is 0 to 1, integration 0 to 1 EXC lambda d lambda. Now notice this is non-interacting kinetic energy, because this is calculated from the non-interacting system. This is the external potential, this is Hartree. So this includes everything, the kinetic energy part and everything. And this is my EXC DFT. If you rigorously derive it, and if I could do everything correctly, this will be my EXC DFT. Any questions so far? Any questions? If none, so let's write this. EXC DFT is equal to 0 to 1 psi lambda VEE psi lambda minus E Hartree rho T lambda. All right? Now we are going to do one thing. Approximation 1. Without knowing what this looks like, I'll just say 0 to 1 psi lambda VEE psi lambda d lambda is approximated as psi 0 VEE psi 0 plus psi, the true psi 1, let's write, VEE, let's write psi 1. It's like this. I've approximated this by a line, and I've taken this and calculated this area. This is my EXC lambda versus lambda. This is lambda equals 0, right? Lambda equals 0, lambda equals 1. Added this and did half. I'm approximating an integral. Huh? Sure, but I'm just making a first approximation. I mean, if I'm saying I'm making an approximation, you can't say you make only approximation that I like. Yeah, right, or making it linear. Now, what is psi 0? Kohn-Sham Slater determinant. So, if I take expectation value of electron-electron interaction with respect to Slater determinant, what do I get? If I take expectation value of this term 1 over Ri minus Rj, Ij 1/2 with respect to a Slater determinant, what do I get? What do I get? सौरभ पाल का लेक्चर भी सुन लिया, सब सुन लिया, CCSD भी कर दिया, सब कुछ कर दिया. और स्लेटर डिटर्मिनेंट का जो है, हाँ, what? Hartree? No. Hartree I have already subtracted. Hartree plus something. Single Slater determinant, never ever. Otherwise, Saurabh Pal will not like you if you say a correlation. Yeah, only the first determinant. No, I appreciate your trying to understand, but I have to answer you also. No, but it has a determinant. I don't care whether Kohn-Sham, it's a determinant. What does it give you? So one part is Hartree. And all this has the same density. What else? Only the exchange expression from Kohn-Sham orbitals. So 1/2 E exchange Hartree-Fock expression from phi I Kohn-Sham. And plus from here also you get 1/2 E Hartree plus the EXC quantum mechanical, right? Rho. Okay. Now if I combine these two, this and this fellow cancels. So you get 1/2 E exchange Hartree-Fock expression with phi I Kohn-Sham plus 1/2, and I'm going to approximate this, EXC d density function approximation. And what do you get? It's a hybrid. It's a half-half hybrid. That is what Becky proposed. It comes from adiabatic connection. All right? And now you can say, I don't want, like you were saying, I don't want to take these at this point, I want to make it different ratios and all that. So you can do that and you'll get different coefficients, but the idea is the same. This can also be now extended. You see, we took VEE to be lambda over R minus R prime. Instead of this, I can take it to be e raised to minus lambda r by r plus 1 minus e raised to minus lambda r by r. Okay? I can choose lambda any way I like. This becomes short range. This becomes long range. And a similar exercise can be carried through, and one can show that at lambda somewhere between 0 and 1, you can reproduce the exact exchange correlation. And that was a paper by Roy, Baer, and Neuhauser, PRL in 2005. I don't remember the exact numbers. Okay, and that is beginning of range separated exchange correlation function. Because now you will choose a lambda, and then you are actually mixing short and long range, and then you do similar kind of, but the idea is the same. Yes, because range separated, one thing that happens because long range part by design, because long range part 1 over r comes out to be correct. In hybrid, for example, if I take the potential out here, long range will come out to be 0.5 by r, whereas here long range part will always give you 1 by r. Yeah, because local excitation depends on the short range, where you are still making density functional approximation. Yes. Transition metal again because you are localized orbitals. So you are making essentially density functional approximation. All right. So, huh? Yes, so HSE was designed particularly for getting the band gaps right. But remember, DFT gives, and this nobody has studied, now papers are coming out, DFT was designed to give you correct density, not band gaps. So if you correct the band gaps, your density may go haywire. So you design similarly with this Becky Johnson and all that, you tune it to get the band gaps right. But band gaps, okay, now I'll do the band gap problem also. Band gaps will, if you correct the band gap, density will go bad. Because by definition, it's supposed to give you the density. And if you do cone-sham correctly, band gaps will never come out right. Okay, so now I'll give you the band gap problem, the jump of exchange correlation potential, right? And nobody earned a chocolate on this. Okay. Okay, now let's do the derivative discontinuity. The first thing I'm going to write in this is, it is generally true that if I take from the same potential En plus 1, in fact, it is true over the entire periodic table, minus 1, minus 2 En is greater than 0. Which makes sense because electron-electron interaction is, it's a positive number. So what it does is, if I were to plot it, if your E, this is N minus 1, this is N, this is N plus 1, right? This is how it looks. It goes like this. All right. So this line, if I add this line, it'll be greater than 0. Or if you want to write it mathematically, you would write that lambda En plus 1 plus 1 minus lambda En minus 1 would be greater than 2En. Is that okay? That should be okay. This is a convexity condition, right? Yeah. Let me, not be adventurous. Let me write it like that. That's sufficient for us. That's good enough. Okay. Now go like this. We want to create fractional DFT for fractional number of electrons. Why do we want to do that? We want to do that because remember, when I'm calculating E, we had E, a functional, which when minimized was, we did this, mu integration rho r dr equals 0, right? This was the condition. And therefore, you get delta E, delta rho equals mu. And if I multiply by some small delta rho, integrate, you get this is equal to mu delta n, and this is delta E. So you get mu equals delta E delta n. Now when Professor Chattaraj was discussing this thing, he said, as a chemist, I'll take delta n to be 1, right? If I take delta n to be 1, that's fine, but you can also have situations, for example, if I take, and you can do this calculation if you do the atomic calculations, Na and a Cl atom, right? And if I were to plot and do an LDA calculation on both, if I were to plot N versus E, and let's say this is 11 in neutral, this is 17 in neutral, you get a minimum which is somewhere, so this is N on Na, right? Which comes out to be somewhere between, some 10.5 or 10.7 or something like that. And the problem is that mu, if you define as chemical potential, a system can partial electrons be transferred to other side, and you can lower the energy. And that transfer need not be 1 electron. And other thing is, again, in chemistry, if I'm forming a molecule, and if I want to think of these two atoms, the minimization of the equilibrium can come when partially an electron has transferred here, sharing time between the two. And I need to define functionals for that. So I need to define functionals for fractional number of electrons to describe such open systems. If I can treat these in a molecule as two open systems, I need to define this, to find the equilibrium. Am I making a correct statement, Pratik? Okay. Any comment, questions on that? Yes. Of course. Here, N of Na. So it should have been, suppose this is 11, it should have been minimum here, it can become before that. So it has transferred some electrons, 0.3 electron to chlorine. This is N of Na. I mean, I've just wrote 10.7, it could be something else, I have not done an exact calculation. Then it would have 11 electrons. N on what? Yeah, so I'm not making a molecule yet, they're far away. Even then. Okay? Alright. So I want to develop this. How do I develop this? So to develop, E rho for fractional number of electrons, right? we use ensemble mixing. That's what we do in StatMech. And that I'll do at t equals 0 because we are talking about ground states. Okay? Now we are constructing this. It is not yet known, we are constructing this. So what would I do? Suppose I have number of electrons n plus omega. Okay? I would have this equal to probability of having n electrons times n, where n goes from 0 to infinity, such that summation Pn is 1. Alright? So I'll do a quick kind of calculate details. You can look in the paper he's going to share. I'm going to write E n plus omega as equal to summation Pn En. This n is not okay because this n is coming here. Let me write this as m. Alright, m is an m index. And what do I want? I want the delta E n plus omega, if I vary these p's, right, should be 0 with these conditions. So what do I do for that? I do delta of summation Pm Em minus a Lagrange multiplier lambda summation Pm minus another Lagrange multiplier mu summation Pm M equal to 0. This is a very funny minimization, but nonetheless we'll work on it. In that this is a linear thing. Linear things always minimize if you at the ends. If it is a right, but we will see. I just want to make it 0 right now. The variation should be 0. All right? Is the idea clear? I'm minimizing or I'm making the variation of the energy 0, and that will be the stable point. So what I'm going to do is this gives me and you'll see how I develop my argument. This gives me summation delta Pm Em minus lambda minus mu m equal to 0. Yes?
Here we are fixing the external potential as same, the boundary condition as same, only changing
The number, only the number.
and by this minimization we are
I'm making it stationary.
actually trying to find the best probabilities of m.
Absolutely. So that I get that number and this variation at that number is 0. Okay. Now you see, if I do this and I assume these are arbitrary, then I'm going to have Em minus lambda minus mu m equal to 0, m tending to a lot of numbers. But I have only two variables, two constants to fix. So at best I can satisfy it for two equations, two numbers, right? So this, let me first write m equals 0 all the way up to infinity, but I have only lambda and mu to fix at my disposal. Therefore, I can do it at best for two numbers, two equations. So I'll take this as E. Pratim, मैं डिस्टर्ब हो रहा हूं. M1 minus lambda minus mu, this stuff where I have to concentrate, is equal to 0, and E M2 minus lambda minus mu M2 equal to 0. These are the only two equations, that's it. Because I have only lambda and mu at my disposed. Otherwise, I'll have to. That's what we're doing here. All right, so I have only two numbers. Only two numbers, right? Now let's see what those numbers can be. And that's where this becomes very important. Can I mix, suppose I want to get a number here. Can I mix this and this? If I mix these and I mix them linearly, I'll get a number somewhere here, which will be higher than any number in between. So I cannot mix numbers which are far away. I have to mix adjacent numbers. Anytime I mix numbers which are far away, see, suppose I mix n minus 1 and n plus 1. Then I can also choose my mixing coefficient such that I get n and I'll get the energy right here, which is higher. So I can't choose that. I have to choose adjacent ones. If I choose even farther, I can fix those omegas such that I get a number in between. And again, the energy will be higher. So I have to, so this implies this plus En plus 1 plus En minus 1 minus 2 En gives 2 adjacent numbers can be mixed. Also, I mean, if I mix other numbers, I'll generate some energy for in between, but I can't dictate that should be the energy. This energy is something else, which is lower. So, if I mix two adjacent numbers, what do I get? So, I have to have then, if my n plus w is here, I'll mix this number and this number. If n plus w is here, I'll mix this number and this number. That's it. Right? So, what you get is that E, you can check this, n plus omega equals, I take this from n and add omega to n, En plus 1. You can check. So, these are those PNs, Pn, Pn plus 1, the probability. You can check that 1 minus omega n plus omega n plus 1 is precisely n plus omega. It is 1. N omega cancels. N is 1 minus omega. So minus omega, omega cancels, and I get n plus omega. No, this is omega. You take omega from here and put it there. This has to add to 1. PNs have to add to 1. Okay. Now, this is what it is. So, now you plot the energy. This is what you get. N minus 1, N, and N plus 1. This is the energy. This is how it's going to vary. That's the origin of that plot. Okay? And this is proved rigorously, taking everything into account. Okay? Now you can also check, I'll leave it for you, that if you put this in, this comes out to be 0 for both n and n plus 1. So that part is okay. And this also gives, you can either calculate mu from there or from here. Mu equals dE d omega, and that is minus En plus En plus 1, which is minus A, or ionization potential for the upper one. If I take n minus 1, E of n minus 1 plus omega will be equal to 1 minus omega n minus En minus 1 plus omega En, and this will give you dE d omega equals minus En minus 1 plus En, which is minus I. Slope out here is minus I, slope out here is minus A. This is rigorously derived for fractional number of electrons. Okay, so mu jumps from here to here. And you may ask, what is mu exactly at n? Right, now this is I, so that means between this and this is minus I, but it cannot suddenly happen that, so it is related to property of n electrons. So even at n it will remain I, it's property of n electrons. And then once you cross n it jumps, because it becomes the property of n plus 1 electrons. So I'm going to write therefore that mu is equal to minus I for m between n minus 1 and n, and minus A for m between n and n plus 1. So I'm putting that equal sign here. Okay. Now, so this is for the total energy. It also, so there's something called, which I'm not covering, Janak's theorem, which says E over E and I equals epsilon I. So if I take the highest occupied orbitals, or n homo, this is E homo. And this by definition is mu. And this by definition will be this. So in an exact DFT, the highest occupied orbital energy also comes out to be exact ionization potential. This is an added benefit. Nobody created it for this, but then one learns. All right? Now from this, we'll go to jump in the exchange correlation potential. Okay, so now we got this d omega or dN is mu, right? And hardness is how much a particle resists the change in its chemical potential, how much it is stable with respect to change in the number of electrons. If hardness is very large, then mu doesn't change. That means it is not going to accept or reject many electrons, right? So d mu, dN or d omega becomes the hardness, chemical hardness, right? And that now you can see is going to be I minus A. It's what he did, he kind of put a second order curve through this. Now we are talking about how I and A change through a number. This hardness will also come out to be band gap then. All right? Yes. Well, that there we wrote in terms of V, not N, which was a different story. That was with respect to the potentials. Here it's with respect to N. But this, so your question is very good, except that this is with respect to N and it is related to the Coulomb-Coulomb interaction being positive. All right? Huh? This is observed. There's no exception to it. Look over the entire periodic table, look over any molecule, this is observed. A generally comes out to be roughly 0. Ionization potential is always positive. So you can, because this, where is that equation? This is equivalent to I minus A being greater than 0. En minus 1 minus En is I. The other one is A. So ionization potential of a system is always greater than the affinity. Affinity means you're putting in charge. It may not accept it, but ionization requires energy. All right? And that's your hardness also. So hardness is always greater than 0. Okay? So should I go to the exchange correlation potential jump now? Huh? I thought you guys take pictures. Okay. Now from this we'll come to the jump in exchange correlation potential. I'll do it through an example. Now for that, I'll also, which I'm not proving, but related to non-interacting system, if I have a system, the density as R becomes very large, roughly goes as e raised to minus 2 square root of 2 ionization potential R. Should we stop? Okay. Okay, the density goes as e raised to minus this. Remember that. And therefore, if there is a single particle system, then orbital, so let me write this. Now, as R goes to infinity in a cone sham system, so let me just relate this. In a Ks system, right, density R is given as summation I mod phi I R square, right? Where do you think far away, if I have these orbitals, right, epsilon equals something, epsilon 1, epsilon 2, epsilon 3, and HOMO. Which orbital will contribute to the density far away? Do all orbitals contribute? Which one? HOMO. So that means you can say this implies that phi HOMO R square goes, or phi HOMO mod, phi HOMO goes as e raised to minus square root of 2I. So the density, the HOMO, the highest occupied orbital, always decays corresponding to the ionization potential. Also, I know, so this is another proof. I know that phi HOMO R will also go as e raised to minus square root of minus 2 epsilon HOMO R. That is also known. And this implies epsilon HOMO is equal to minus I. This is proof without Janak's theorem. All right. Now, let us look at this. Suppose I have a system, right? Compare this. I have a system, and in this, an electron, another system, n plus some omega electron. Omega is, let's say, a small number, right? Omega is between 1 and 0. Then phi HOMO out here, as R tends to infinity, will go as e raised to minus square root of 2I R, and phi HOMO here will go as e raised to minus square root of 2 AR, where A is the affinity, right? Because this is n plus omega. And why? Because this has energy or the density which is equal to 1 minus omega rho n plus omega rho n plus 1. And as you go far away, which decays faster, this or this? This goes as e raised to minus square root of 2IR. This goes as e raised to minus square root of 2AR. I is always greater than A. Therefore, as you go far away, this is the density that you get. Is the point clear? As you go far away, it's the higher end density that will dominate. Okay. I can also write, so now let me demonstrate through. Yes.
to supply some energy to an electron to some other. It's not necessarily always.
Yeah, so I'm taking either A to be 0 or negative. So I minus A still remains greater than 0.
In general, what happens? You get energy is released when an electron.
Yes, that's the affinity.
But there are several systems
Yeah.
where energy is.
So I'll take it to be 0. It's not even accepting. So I'll take A to be 0. Yeah. So. Okay. So in that system, the electron is kind of free. You can think of it like this. Right. But let's take it to be bound right now. Just to. Now, you see, if take a 2 electron system, let me take H with 1 electron and hydrogen with 1 plus omega electrons. Okay. Both will be in the same orbital, right? So I'm taking this system because here some calculation becomes easy. So in this case, I have minus 1/2 del square phi plus V external plus V Hartree plus V exchange correlation equals epsilon V exchange correlation. Phi equals epsilon V exchange correlation. Phi. So I can write as which one? Oh yeah. So I can write Vxc R as R tends to infinity as 1/2 del square phi plus some constant, where constant is chosen so that Vxr goes to 0 far away. Is that okay? We take the reference to be 0 far away. That's how we define our ionization energy, epsilon and all that. Okay. Because these terms go to 0 or V Hartree V external anyway will cancel. All right. So now, in this case, phi homo for H 1 plus delta as R tends to infinity is going as e raised to minus the square root of 2AR. So Vxc R tending to infinity will go as, you can calculate double derivative as R tends to infinity will be 2A divided by 2 will be A plus some constant. Oh, that is omega, yeah. Sorry. All right. And phi homo H1 Vxcr tending to infinity will go as I plus constant. From this. Are you with me? Okay. Now, you can also see that, so can I erase this? This we have already worked out. And when does, okay, and rho inside I'll define for H 1 plus omega, right, is 1 plus omega, 1 minus omega rho hydrogen 1 plus omega rho hydrogen 1, 2, right, will be roughly rho hydrogen 1. Let me define what does it mean. Okay, I'll do that in a minute. So what you're going to see, if I were to invert this exchange correlation potential according to that, for hydrogen it is going like this, where this is I. I'll adjust that constant to bring it down. For H minus, inside the orbitals is roughly the same because H minus, H1, right? Because inside the density is roughly the same and phi is root rho. Inside, the exchange correlation potential will go like this, where this is A. Are you with me? Okay. How's this is for H1 plus omega, okay? This is for H and this is for H1 plus omega. For H1 plus omega, what is the orbital far outside? Is this. And I already said that Vxc as r goes to infinity goes to A plus constant. Right? So this is A. It goes to A. And this goes to I. And inside is roughly the same. Okay, in fact, it will be quite the same, quite some distance. Now I want to make it 0. So what would I do? I'll bring it down. Let me use the same color. And I'll bring that down, make it 0 here. I have to bring it down by I. Right? So I now want to erase this. So if both the potential go to 0 far away, there's a gap. And if you plot the difference, it comes out to be this difference, which is like this. You bring delta is smaller and smaller, this guy goes outer and outer. And we'll work it out how far does it go. Far away it has to go to 0. Inside there is a jump. So exchange correlation potential, even if omega is 10 raised to minus 10, minus 11, minus something, jumps. It changes by a constant inside the system. Okay, now how far is it? So let's say I want phi homo of 1 plus omega system, right, to be larger than phi h for r tending to infinity. All right. How much is this? Okay. This density to be larger than this density. 1 minus omega is roughly 1. Omega is very small. Omega tending to 0. Huh? I'll come in a minute. Let me just. So this I have already said is e raised to minus square root of 2a r. I want this to be greater than phi square root of 2I r. Okay. This tells you e raised to this is twice as much. This, minus square root of 2I minus 2a. Since I'm talking about the density, let me write this mod square. So this will be 2. R is roughly 1 over omega, right? So you can say that R is of the order of log 1 over omega over the square root of 2I minus the square root of 2a. 2. Smaller the omega, farther out R is, beyond which this happens. So this region, let me call this R critical. You make omega smaller and smaller, this R critical keeps going farther and farther out. All right. Now this has connotation. This has. Now you didn't get the jump. Now you see, this potential is going as 1 over R like this. Inside its structure is the same, except it's shifted by I minus A. So if this is for n equals 1 and this is for n equals 1 plus omega, it's the same except that it is changed by I minus A. That's the jump in the potential. All right. So this I've shown through an example of hydrogen. This has now implications for band gap. And the implications for band gaps are this. Yes. Say that again. 1 minus omega, omega is 10 raised to minus 10. How does it matter? It's very small. Ideally, yes, but it doesn't matter. Now, imagine this. I have a conduction band and a valence band, right? This is filled up to here. And I do a cone-sham calculation where I get EC and E valence. This is 10 raised to 23 electrons. All right? And I put 1 electron. What will happen to the exchange correlation potential? It will jump. So I add 1 electron to this. If I add, this jumps, and when something jumps, the eigenvalues also jump. I raise the potential by that. I'll call it delta Xe. All right? Energy coming from here was I. Now I put an electron here. Energy coming from here is A. Right? And I minus A is the fundamental gap. What will it be? It will be this difference. This is the fundamental gap. And now you can see what will this be? This will be equal to EV minus EC plus delta Xc, which is E gap cone sham plus delta Xc. So even if I could do an exact, absolutely exact cone sham calculation, right, I'll get this EV minus EC. But if I add an electron, this fellow jumps up. I'll always underestimate the gap. Always, no matter what. If I tune my potential to correct the gap, my densities will go haywire. Because you're tuning it to get the gap right.
Especially their unoccupied space. Orbitals doesn't make any sense.
Yes.
Somehow get the TTFT excitation energy right, there they get the excitation right, but the orbital, if you see the ground state orbital.
Yes. So they're just getting the eigenvalues correct somehow or the other. But orbital nature one doesn't know. Yes.
I'm confused in the start, at the very start. Seem counterintuitive. Let's say you have an example of say 1 lakh systems of n electrons, and the density far away goes as e to the power minus root 2 IR. And that is say almost universal. So it goes same for all. Now
So you have to just one sec, I'll break you. In quantum mechanics and stat mech, that's the difference. In quantum mechanics, whatever you do for ensemble goes for 1 electron system also. So don't say that some systems are going as e raised to minus 2a and some are going like this. Quantum mechanics is that same system which is behaving like this. That's the difference.
I'm saying that now you bring just one another out of the 1 lakh you have, you add just another to the ensemble with n plus 1 electron.
I have a system of n electrons, one system, and I'm adding some more. That's all.
But we realize omega as a fractional.
But yeah, so I'm doing it with probability, right? But in quantum mechanics, the probability applies to even one system. I'm not doing it through ensemble. I'm calling it ensemble average, but it applies to one system. I can create those systems. You can do that. Okay, I think 6. Okay, I can take some more topic. Any questions, comments on this? This is a. I went through it very slowly. It's a tough topic. Now I did it through one electron. Now you can do it through n electrons also. You can work out that far away the orbital will be the HOMO, and HOMO changes, so the whole thing changes. And I did it through one electron because I could invert and get you that potential. In other systems, I'll have to do it numerically, but the same arguments will be the same.
thing that you're saying, for example, band gap, fixing, trying to fix the band gap is a problem. So, but that's what people do who are trying to scale. But putting, how do we create a functional and as a taking, which will give us correct density? That's a very difficult thing. How do you think we can do that?
No, so those are the functionals which are being created, right? That density, but the moment you try to create a functional which will give you something else, right, you go away from the Kohn-Sham premise. So as long as you're improving functionals through these whatever constraints and everything, density will become better and better. It need not. But if you fix other properties, then there's a problem. In fact, now the papers are coming which are analyzing this because now people have Monte Carlo densities available for solids, so they invert and do it. 2023, there's a paper. There's one going to come out now. That I can tell you because I read that. So.
Why the band gap is the benchmark?
It's not a benchmark, but band gap is a property which everybody, any body theorists would be interested in. If I want to design a material, what do you look for in a material? Absorption is one of the things. You look for stiffness depending on how you want to use it. But gap is a very important property because it determines the optical properties. It's not a benchmark, but it's an important property which you want to calculate correctly.
But even if band gap is right, some other properties we are not.
No, so far what we are saying is in any Kohn-Sham system, your system is designed in such a way that it gives the density correctly. If you try to fix band gap, your density will go haywire, your other properties may come out wrong. Dipole moments, for example, or the oscillator resistance may come out very wrong. That's what he's talking about, that if the orbitals are not right.
But as you're doing the wave function based theories is the point idea. Like constant variation activity as you do. Say suppose not only I want to get the energy minimum, but I want to get my dipole moment correct. So there are constant
So the
variational calculation.
yeah, so wave functional theory is different because somehow everything gets connected. Here the only thing you get correctly is the density. That is I and A happen to come out to be right because that's an insight that produce PPL. Yes. Yeah, but then you have to create that functional.
Density function. So if I correct density and I can connect these as a Lagrange with the Lagrange multiplier and do some constant variation, can I get both of them?
No, because those functionals are going to be not related directly. That's the problem. Everything that you do through energy comes out all right. Frequencies come out all right. Stiffness comes out all right. But anything else will not.
But in wave function based picture, there are many.
Yeah. You do polarizability, the Dalgarno method and all those things.
Very good example.
Yeah.
Very good dipole moment wave function also. See, you said density is changing, right? So what is the disadvantage of it?
What?
What is the disadvantage of it?
Disadvantage? No, if you're not getting the density right,
You are not getting anything.
that's like cooking your food wrongly.
What is the reason?
No, you're not getting the point. You're taking it very lightly. The thing is, if you create a functional that gets the band gap correctly, it will spoil the density. So necessarily getting a band gap right is not maybe the right thing to do always.
I'm telling the corollary of past 20 years. It will spoil all other properties. That's all other properties.
Now, people who are doing it are doing through generalized Kohn-Sham also I want to do because it's okay. I mean, the time is, I think, almost up.